Okay. All right, Gina. Okay, now, now I got to go back to my book so I can read it. All right, so 56, so chapter 27, number 56. I'll put here, we're starting at about 3:03. Maybe I can get some time frames down. But the beginning part of this one is the physics, and then there's some tough math in here. So I'm going to start it this way. I'm going to go ahead and lay it on its side. Maybe like this. And so the narrower part, they said, has a radius of A, and the thicker part has a radius of B. And here's really kind of the first part of the physics, if you will, is this chapter 27 says that the resistance is made up of 4 factors. The first is the material, and the second is the temperature of that material. The third is the length of the material, and the fourth is the cross-sectional area. So if they're designing it so that the current would be running, say, in this direction, and so it kind of makes a flare outward, kind of a cone with the tip cut off here. The way to probably think about this is with slices, sort of like you might have slices if you were cutting, I was going to say cut a carrot. This has kind of got a cone shape. So cutting a pointy carrot it would be kind of pointy like this that we might cut. Not sure I have a good analogy to something that tapers like this that we cut, but I'll just go with the carrot. I suppose you could think of it as a stack of coins, where over here is the bigger coin. So here's like a quarter, and then the next would be a nickel, and the next would be a let's go penny, and then a dime. But that's kind of that key. So if I wanted to know the resistance of just kind of this slice, and I said the slice, had a thickness of dx, this might change to something like this. A little bit of resistance would be the material it's made out of times its length, and since the current is going this way, dx, and that's why I wanted to put it on its side to kind of set up my integral with a dx. I thought you'd feel more comfortable with a dx versus a dy. It's probably not that much different. And then this area. And so I would say that's the resistance of one little slice. And of course, then there would be another slice and another slice and another slice and another slice and another slice. And the current would have to go from one into the other, into the other. So this is series. And the way we can combine resistors in series is we add them together. You might think of this as a little resistance number 1, plus a little resistance number 2, plus a little resistance of number 3, ... But I'm hoping what you would mentally get out of this then is this would then be listed in terms of calculus as an integral. And so you would be adding up the resistance of the first slice, let me call it a quarter, and then well, I guess a quarter would be the last one this way. But anyways, the last one's a quarter, the one before that is the nickel, the one before that is the penny, and the one before that is a dime. And so that's what I mean here by this math. I will get the total resistance by adding up the resistance of each little slice. So I would say that that's probably the first big step, is to get really in this position that we're doing an integral. And then put that together with what we said earlier on, which is saying it's rho times dx times the area. Now, of course, we are probably already realizing that each little coin has a bigger cross-sectional area. Obviously, the quarter is bigger than the dime, and and then it gets a little bigger with the penny and a little bigger with the nickel and into the big quarter. So this number is changing. And in fact, this number A is somehow related to this X. Now, it's all the same material, so this number doesn't change the resistivity. In fact, maybe I will just take advantage of that and pull the constant, which is the resistivity of the material. Had they changed the material, that would have been a different story, but they didn't. And so it would be this area. And looking at this as a coin, then the area would be, you know, this surface area across the face of the coin, and that's a circle, so that's a pi r squared. And of course, maybe again, pulling out the constant. Now a little trick of mathematics might come into play here. What is the radius? And this is another reason why I want to kind of lay it on its side. I think you're a little more familiar with mathematical equations where the independent variable is x and y. So as we would be adding these up along x, the dependence, the radius that is, the y would change, and the radius would be this y value. This is a straight line. And so what I'm trying to say and kind of remind you back of your math class is that the equation for a line, y, equals the slope times the position x, add to that the y-intercept. And this y then would really be the r, the radius. That's what it is here. So now I just got to get the slope of this line and the intercept. Maybe I'll start with the easy one, the intercept. Here's the line. It comes down. It intercepts at A. Okay. The slope would be the rise over the run. Well, I didn't put it in this diagram, but the picture shows that the run is the length x. They got it vertically, so its vertical height would be the h. Then the rise would be, you know, the y value here minus the y value here. So that would be a b minus an a. All right, so there's the slope, rise over the run. There's the x, there's the y-intercept, and that's all equal to r. So if I put that into here, this would be b minus a over h times x plus a quantity squared. And then, of course, I would be adding up from x equaling 0 to x equaling h. So there's the, I guess, maybe the first big math step, because now we've got to actually solve this integral. And this one is just kind of screaming at me, u sub. So let me kind of do a u substitution here, call this page 2. But if I let u equal this whole equation, b minus a over h times x plus a, then a du would be b minus a over h times dx. So this integral, r total, which has the rho and the pi in front right here, would now become a u squared down at the bottom. This whole thing is u squared. And then the dx could be h over b minus a du. So that the h can pull out in front to go with the rho. Pi can be joined up with the b minus the a, and then I just have an integral of du over u squared. And so that's our kind of our standard power functions. You might move the u to the top and call it an integral of u to the minus 2 du. because you add 1 to the power, so that'd be a -1, and then you divide by that new power. Now we can debate on our limits. There's 2 ways to do this. Usually I like to just ignore the limits of u and go back to x. This would actually be easier to put in the limits of the u. So maybe I will. So let's talk about the limits of the u. Before I switched to a u, it was a dx, and so the x started at 0. If I come back here and put an x equals to 0, my u would be starting at a, okay, and then my x went to h, right? So if you put in an h here, that would cancel with that h, so h over h, good. So that's just a b minus a plus an a. So the minus a and the plus a would go away, and that would just be a b. So this would become the rho, the h, the pi, the b minus a. I'll leave the -1 there for a second. And I want to think of this as 1 over u. So this would be 1 over b minus a 1 over a. If I get a common denominator, this common denominator would be AB, and this already has a B under it, so this would be an A. And this already has an A under it, so I'd have to multiply by B. Now, if you take that negative with this is a B minus A, and that's what that is. So that negative makes a plus and a minus, B minus A, and then this B minus A would cancel with that B minus A, and then I think we get what they've asked us, rho times h over pi times AB. Yay! So there's our calculus.
Dr. Young, can you explain the limits of integration one more time, please?
Sure. Now, do you mean the limits for the x or the
So
u?
the 0 to h makes sense to me, but okay. I think I got lost when I saw a to b.
Oh, okay. Yeah, I questioned if I should do it this way. I'm gonna stick with it. Tell me if this helps. If not, I'll, because you don't have to figure out what the limits are for the u if you go ahead and replace the u back with what it is equal to, then you're back to being x, and then you can just place your limits of x of 0 to h. And that's interesting enough, mostly how I do it. But this time, just because I saw this coming, I thought I would switch it to the u. So I'll try to explain the u here, and it's back here in this u sub. So in terms of x, you said you understood how the x was going from 0 then to h. Okay. So for the u, we would have to put in the 0 here for the x and see what we get. So if I put in a 0 for the x, this first term is 0, and then just plus a. So what I'm saying here is when x is equal to 0, u is equal to a. Now, when x is equal to h, so let me put an h in here. If I put an h right here where this x is, I'll cross that out. This h would cancel with that h down there. Then this would just be a b minus an a, and then I would still have this plus a. And of course, that minus a and that plus a would cancel, and you'd be just left with a b. So the limits, if you're talking about x, are 0 to h. If you're talking about u, it's a to b. And so that's why I just put an a to b for my limits of my u. But I could have just as easily switched the u back to its equation for x and then had the limits of 0 to h for the x.
Okay. Are you able to open up the author's solution to 56 and explain the very first step that they have?
Sure. Yeah, that sounds like a good question. Yeah, somebody else had questioned the author's solutions, and not that they were wrong, but they're not always the most enlightening. And I was telling them, and I will tell you, that yeah, I think what they do probably to save some money is they're paying an author to write the book, a bunch of authors, and then proofreaders and all that, and then to make the solution manual. I think they often go out and just hire a bunch of graduate students who need some money and say, hey, can you work out these solutions? And sadly, I don't know what happened to my phone. Try the connection again. I checked my settings. I thought earlier today I told it to never go to sleep. Well, that could be a problem. Where's the display? Here we go. Display and brightness. Auto lock. Yeah, never. Yeah, I'm not sure what happened exactly. Hopefully that won't happen again. Okay, sorry, Gina. So what I was saying here is that the graduate students who often do it, they take some creative steps or some big steps. They just don't always do it in a way, and this might be one of them. I don't know yet. I'm going to look here. That maybe is the most enlightening and helpful to somebody who's trying to understand what's going on. They just get the answer. So usually, a lot of times, the answers are right. They're just not always written out in a way that you're asking about. Is just the best way to get to it. So let's see. Right now, I've called up the solution page. Let me just click on chapter 27, and we'll scroll way down here to 56. Oh, I see what they did. Okay. So,
quick question.
Yeah.
So, as far as what they did in the solution manual, you're saying that the way that they're doing it in the book sometimes isn't necessarily the same as the way someone who's actually taking the course maybe would think of trying to solve the problem.
Yeah, that's certainly one way. But I do agree with that. But I would also say more than that was they do such big steps, probably to make the printing of the solution manual smaller, that it can be a little intimidating for the beginning student to say, oh, I was supposed to figure all that out in one big step. And no, that's like 5 steps or something. So it's a little of both of those, if that helps. But like any problem, there's many ways usually to do it. So good questions. Yeah. Okay, now so Gina, back to you. All right, so okay, so I see as I look at his line 2, and of course you're asking about line 1, but as I look at line number 2, he's got exactly this. Okay, and he got there a little different. If you just recall how I got there, I just made a grid and looked at this line and said, well, that line would be the radius, and the equation for a line is its slope and its intercept. Okay. What your author did was, and I'll try to draw it out, instead of algebra, your author did a geometry. And he did something like this. Let me draw the cone again. And I'll draw a line down the center of the cone. Maybe I should do it in blue. Call that the vertical axis, the horizontal axis. And your author did something like this. He said, if you kind of extend this line out until they meet, you have a triangle here, okay? Oh, no, he didn't quite do that triangle, did he? Okay, let me try that again. He does this triangle. So the length of the base of this would be h, and the height of it would be b over a. And then says, if you were to do this, if you were to move some distance out, if I can see a little different color in the black, and maybe draw a vertical line here, this triangle in black is similar in shape, but smaller in size than this full big triangle in blue. And so if we call this height right here, say y, he says using geometry, using similar triangles, y is to, and then of course we've come out a distance x, as the full height, which is b minus a, is to the full length. So he uses a set of similar triangles. Then he moves the x to this side and says then y would be b minus a over h times x. Then he does one more step here and says, well, now the radius would be this little height y plus this height, which is the a from this beginning distance. So it would be the y plus the a. And the y we just did, so that would be b minus a over h times x plus a. So that's how apparently the author got the radius. Because he starts off by says, from geometry of the longitudinal section of the rectangle shown in the figure, we see that. And I don't know if that's so easy to see, to be honest. So if you're having trouble seeing how he got that, I totally get it. Clearly it's some geometry, and he even writes geometry. So I thought he was going to, even I thought, hey, he's going to do this triangle. But then as I looked at his equation, it wasn't. It was more this triangle. So, did that help?
It does. I think he's still got his on the y-axis.
Oh, yeah, sorry about that. So I still turned mine on its side. So yes. Just, yeah, sorry, I overlooked that little subtlety. I hope that didn't bother you. I was focusing on the geometry, but you're right. Tilting it this way would have then made this an X here. And of course would have made this then a Y. And so I really should switch these around to match him. So this would be an X and this would be a Y, even going all the way back to here. This would be an X and this would be a Y. So I'd make that the X and this the Y. So the radius would be X plus the A, where the X is B minus A over H times Y plus the A. Mm-hmm. And so that means when I go to do my integral, which is this dr, it would look like rho dy over rho, and the area would be the pi r squared dy. And then again, the rho would come out, the pi would come out, and you would have a dy here. And then the r would be this b minus a over h times y plus an a, and then that would be squared. And then the y would be going from 0 to h. So this is the same integral we had. We just wrote it in terms of x's instead of y's. And that's exactly why I turned it on its side. I hope that wasn't confusing. Let me know if it will. When somebody else asks, I won't tilt it. I thought that would be more helpful to tilt it and to leave it the way he did it, so that we would have things in terms of dx. And I think that's a little more what you're used to seeing in calculus.
I agree. I'm glad you tilted it.
Okay, good. Yeah, and then of course, then everything beyond that, other than he uses y's instead of x's, is exactly the same. In fact, also, I don't know if he even does a u sub. He does do a u sub. He doesn't substitute the whole thing. What does he call u? He doesn't make it real clear what he's calling a u. He's got a. So he becomes an AU plus B. So there's the B. So I think his U is a Y over H. It doesn't seem clear. I'm not sure what he's doing for his U. Guess we could figure it out here, because again, these are some big steps that make it kind of hard, but he's got AU plus B in one step where he says using the integral, and he's putting that in place. Oh, du. And he's putting that in place of A minus B times a Y over H plus AB. So I'm pretty sure he's calling U an A minus B YH.
And where does he get the AU from?
Oh, well, I mean, I'll give it a try. Yeah, I don't completely see it, but let me do this. I guess I'm kind of questioning the value in, in his use of. But I'm gonna give it a try here. Let's say that I have an integral. Well, let's say this is my u sub, because I have this integral that is the integral of a dy, and then it is a AB y over h plus b squared. So if this is my guess, I'm not 100% sure if that's what he's doing, but if he calls that u, then this, well, then I need my du. So then my du would be a minus b a minus b over h dy. So if I do my U sub, in the bottom, if that's my U, I would have a U plus B squared. And in the top, I would have, in place of a dy, I would have an H over an A minus B dy. That is not quite what he has. He's got an AU squared. Oh, so that's not his U sub.
Would it help if you distributed the y over h to the a minus b first? I mean, it looks like that would be your first step, at least. I just don't see how he gets it from there.
I don't either. Okay, I'll keep going. I mean,
I don't want to tap all the time for this, but it's confusing for sure. I'm with you on that.
Huh. Actually, maybe he's doing something a little more creative. And he's not really specifying what the U is. Yeah, I think, okay. We could go back, try to keep going in reverse engineering, but I think that's, and I will if you want me to, but I think that's a mistake. I think he's doing this. He's saying that we have an integral that we want to solve that looks like this. dy equals a minus b, y over h plus ab, and then we square it. Okay? Yeah, I think this is what he's doing, and this is kind of confusing. And he says, let's pause from this for a second. Let's look at an integral. And so he doesn't want to confuse you. And so instead of calling it a y, he says, well, let's just call it something different. Because you could think of this bottom one as some kind of coefficient times then the variable y times some kind of constant, and that whole thing squared. But here's where his solution, I think, gets a little confusing. He deliberately changed this to a u so you wouldn't think that the u had to be a y, but it could be. But he also did this. He carelessly, I think, but he puts an a, and you're going to think that this a is the same as that a. At least I was. I don't know if you were. And you're going to think this b is the same as that b. And that is not at all what he's trying to say. What he's just trying to say is if you actually do this integral, okay, you get a minus 1 over this a, then this a u plus b and what's that little prime mark? Oh, that's a comma. Okay, never mind. Comma. That's the end of the, before he goes on to the final solution. Okay, so now let me pause right there because I think this is the confusing part of the solution. Although, at least to me, apparently the first step for Gina was more of the confusion part. But this one here, when I saw this, I thought the author was trying to do a U sub when he went from here to here. And I don't think that anymore. I think the author is saying, I'm going to forget about this problem for just a second. And I'm going to look at this integral, and I'm just going to go look it up. I'm not going to actually solve it. I'm just going to go right to the appendix B, and I'm going to look it up. Now, we could solve it with a U sub, but I don't think he is. And I think he's making a little mistake because he's using the symbols A and B, but they're also used up here. And so because of that, you might think that his A here means that A, and it does not. And you might think this B here means that B. It does not. He says, if this is the answer, let's do a comparison between these two. So if the U in this equation is switched to a Y, and the A in this equation is switched to an A minus B over H, and the B in this equation is switched to a B, so in that case, the B is the B, then I would say this integral that I really want to solve is a lot like that one. See, this B is like that B. The stuff in front of the Y is this. And so if this is the answer, then right here, this A would be A minus B over H times A minus B over H times Y plus B, and then evaluated with your limits of 0 to, he goes down, so I bet it's a minus H. Oh no, because he switched order, so 0 to H. So he's saying that this integral looks a lot like this one. So let's just take the solution from appendix B and let's put in the comparison. And so you're going to get a 1 over. And so if we put in actually, why don't I just move this so that it's an H over an A minus B. So I'll move that in front, okay. And so then I'll have a 1 over, and so I'll put in my H. And then, of course, when you put in an H, this H would cancel with that H. Then you would have an A minus B plus AB, so that's an A. And then you would have then minus 1 over, and if you put in 0, you get a B. So this was I think, kind of a weird way, because he didn't actually solve the integral. He did a comparison between one that's already have been solved, but that A threw me off. I thought he meant by this A, it was the same as that A, and he had done a U sub. So I don't like that, but maybe that's better for you. So I would say that's the integral. So now if you go back to his solution where he has this rho over pi times this integral that we have essentially done here, you now would get this rho over pi. Then you would have this H times this A minus B. And then you would get a common denominator of A and B. And then you would have this B minus A. And then you would get a rho and an H, you would get a pi, you'd get an AB. And if I look carefully at this, you get a negative. Which again makes me wonder if I made a math there. Oh, I did. This had a negative up there. Yeah. Okay. So I was so busy with the A and the B, I forgot that negative. So that negative would go all the way down and finish off with that. Wow. Okay. If that's more enlightening to you, fine. But the fact that he puts a U up there and an A up there made me think right away that he was doing a U sub, and that is not at all what he's doing. I personally preferred the way I did it, but you make that call. Glad we saw both.
Yeah, I think things like this is why I've struggled with the calculus and these problems so many times.
Yeah, things like that. But it's definitely going to make you style.
Yeah.
Although I gotta admit, if you work through it like I just did, it might be frying your brain. But it's like one of these things that if you make it to the other side, you're actually better off for it. But it might be so hard you don't make it to the other side.
Yeah, I get that feeling.
Is there a question from 27?
Okay. Okay. Sure. And let me just check, make sure. Was there anything in the chat room?
Yeah, there is one.
Oh, so let me.
Oh, I was just wondering, the question you were talking about, is it from chapter 27?
Oh, that's what you're asking. I thought. Sorry, I thought I heard you say, "Is this?" Anyways, yes, this was from chapter 27, number 56. So technically, it was last week's homework, but it was a tough one. So I understand why some people maybe haven't been able to finish it up yet.
Okay, thanks.
Yeah. Okay, so maybe that's enough time trying to figure out what the heck the author was doing. I hope that was going to be enlightening for some of you. All right, so Anthony's asking him. Let me write it down so I can put that in the video when I send it out. So 28, looks like we have an RC time constant, and it's number 31. And you're really asking about part B. I might have to do part A just so I can get to part B, but also maybe that would be better if I had it on video that way. So I might make that call. But yes, let's do that one. And let me write down a time. What is it? About 3:45. 3:45. So number 31, chapter 28. I'll just scribble out part B because maybe or maybe not I'll do part B here. Okay, so I need to switch back over to the either the textbook or this page. Let me go backwards, and when I switch chapters, it makes my PDF so small. All right, so there's 100% back. I can see it. Oh, yes. Gotta love this one. And I think I. All right. Well, I think I'm going to make sense out of this, need to do an A here. But it says this circuit has been connected for a long time. Now,
that means that the capacitor is fully charged, right?
Okay.
Is that what that's implying?
Yes. And let me give a warning. That does not mean it's fully charged to 10 volts.
Yeah.
Okay. All right. So I'm going to maybe help out. I hope this helps and doesn't hurt my your understanding. I'm going to change my drawing because the current comes up and splits into a 1 ohm resistor and an 8 ohm resistor. And the way the author has it drawn with this kind of vortex or vertex here at the top, I don't really see that same thing in my drawing, but I see a better parallel connection. And so that's kind of what I'm after, or maybe a better one. So let me do a slight modification that would be the same circuit, but might help with you kind of comprehending. Because again, notice the currents here can split and go either through the 1 or the 8. And then also notice, again, I didn't draw the 2 and the 4 hooked together, but they really are. There's just a wire connecting. So there's a little space between them, but there's no resistance, no voltage change. So I'm trying to convince you that the drawing I have right now is the same as that drawing. And the reason I'm trying to do that is because, you know, part A, which says, what is the potential difference across the capacitor? They're really saying is, what is the voltage at A and compare it to the voltage at B? What is the voltage difference between those two? And as I'll lost track of who asked this. I think it was Anthony. So Anthony, you asked it, but somebody else jumped in. Maybe that was you, Anthony, who jumped in and said it would reach its it would be fully charged after.
Yeah, that was me.
Okay. So yes, that's a big concept, and that was kind of my hint I wanted to leave you and everybody else was, if you ever read any of these problems and say it's been hooked up for a long time, here's what they're trying to say. They're trying to say that the current has been flowing, and in this case, what happened is the current would flow, and then some of it would split off at this point and go through resistor 1. The rest of it would continue on and go down to 8. Then, depending on how things were connected, the current's going to go across the capacitor at first. So at first, I'll just say it's flowing from A to B. And I want to emphasize, I don't really know if it would flow from A to B or B to A. But I know at first, while the capacitor is charging up, there would be this flow. And of course, in this case, then these two would come together and go through resistor 4. And then the stuff that came down 8, and then some of it split off, the stuff that didn't split off would come down through number 2, okay? But for part A, the magical step is to say, after a long period of time, we can conclude that there's no current through that part of the circuit. The capacitor has been full. And so if you want to redraw this as an 8, a 1, a 2, and a 4, and this is the key, no connection between A and B.
Oh, Dr. Young, your iPhone screen froze again.
Oh, thank you. Heck. Okay. So the iPhone seems to be fine. Let me do a stop share on the Zoom for a second and reinitiate it. See what that does. All right. Bluetooth 9. Okay, we're back. Thank you, Gina. Okay, so no, froze again. Come back.
Oh, there. It's oh, is it behind?
It is. I'm gonna try something. I'm gonna start writing some numbers on the page. Ready, begin. 0, 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,008. Oh yeah, so we're about 7 seconds down. That's maybe. Let me at least take a moment to try to fix that. If we have to deal with it, we will, but it's a little much. Stop sharing again.
You think it's because it's been, your iPhone's been doing the video all day, so it's like kind of just glitching out now?
Well, very well could be. Should I?
You could try turning off the your face camera. Maybe it's a bandwidth issue. I don't know.
Yeah.
Or if that doesn't work, you could try just leaving the meeting with your iPhone and then joining back.
You can also double tap the home button and close everything else except for the thing you're using.
Okay. Yeah, let me try that one first because it seemed to be the shortest one. So I closed every other app. And
if that doesn't work when I'm tutoring, normally just ending Zoom and then starting it again on the device normally works too.
Okay, yeah, then that happened one time before where I had to close the Zoom, and I was avoiding that one, but we might have to do that one. All right, well, it looks like it's pretty live now. 0, 1, 1,000, 2, 1,000. All right, let's see what happens here. Okay.
Between 1 and 2 seconds.
So, yeah, so it's actually yeah, less than 1 second delay. Pretty much. I'll move my hand now. I'll bring it back now. at least on mine, and I suspect that
It's getting better.
Looks good to me.
More I see it, yeah.
Okay. All right. So I'll keep going. Let me know if it freezes on me because I'll mostly be looking at my paper. Okay. So what I was trying to say here in part A was that besides what you had said, Anthony, that it would be full, it would also imply that there's no current going through the capacitor anymore.
Yeah.
So when it, okay, good. So I think you see where I'm headed.
Yeah,
I
so
could
that's
look at
they're
this.
just parallel, right?
Right. So check this out. This, I didn't write down the 10 volts here, but they gave me an 8 and a 2 on this side. So that would be in series of 10. This side was a 1 and a 4. So that would be a 5. So if I kind of redraw that as a 5 and a 10, in fact, you might even be tempted to group these together, but let me not, because if I just wanted to know, say, the current in this first branch here, I would do something like this. If I called this current number 1 and I did a loop, this would be a 10, and I'd go with the current, so it'd be minus. The resistance would be 5 I1, and that has to equal 0. So that one alone would give me a current of 2 amps. So I know that in this, I'll call it the middle branch, I get 2 amps. And if I did the bigger loop, which I think I was telling you guys in the last sessions, I like to do the 2 smaller loops, but in this case, an exception, because if I do this bigger branch and call this current that's on the right, number 2, I would do a loop and I'd go 10, and I'd go with the current, so it'd be minus, and the resistance would be 10, and the current would be 2, I2, and that would complete the loop, so that would be 0. And so current number 2 would just be a 1 amp. So I don't have any like those real complicated ones. We had like 3 coupled equations, 3 equations, 3 unknowns, or 4 equations and 4 unknowns.
I think you may have mislabeled your I1 in the first solution there. Is that I1?
Thank you. Yep.
You're welcome.
I'm glad you guys are keeping me honest. Thanks, Gina. All right. Okay, yeah, that's supposed to be I1. So the middle branch is 2 amps. The right branch here is 1 amp. And the reason that is helpful is when I come back to, and I'll kind of mentally forget about this equivalent one for just a second. But I'll come back to this one, the one that I've drawn without the capacitor in. And now that I realize that over here there is 1 amp going down, and over here there is 2 amps going down, I could do something like this. Since again, the question was before this, what does it say? What is the potential difference? A right here can be thought of as this. It would be an increase of 10 and a decrease, and then I would just have to go current times resistance. So maybe I would write it this way. The voltage at A would be an increase of 10 minus the current, 1, times the resistance of 8. And so that's 10 minus 8, and that is then 2 volts.
Yeah, that's exactly what I did. I just did the.
Okay. Oh yeah, and I totally forgot. Yeah, you weren't even asking about A. You said for B. So let me real quickly then go and get the value at B. So the value at B would be, let's see, 10 minus the current, which is 2, times the resistance of 1, and so that's an 8 volts. So the voltage between them would be the 8 minus the 2 would be the 6 volts. So that's just, I guess, for people who want to see the video, or if any of you wanted to see that, if you haven't done it yet. So that would be the answer to A. What is the voltage difference between A and B? But now it says, if the battery is disconnected from the circuit, over what time interval does the capacitor discharge to 1/10 of its value? All right. So now, and then I'll come back to the original circuit, we're asked to now remove this. Okay, so let me redraw this, starting with the capacitor. So the capacitor is here. And remember then, we just concluded from A that we have charged it up to 6 volts. We might even ask ourselves which one was bigger. Remember, point B was at 8 volts. And then point A was at the 2 volts. So in other words, this side of the capacitor has the positive charges on it, and this side has the negative charges on it. And if we redraw this capacitor then would be discharging across the 1 and then the 8. So this is a 1 and then an 8. But at the same time, in parallel with it, it would be discharging through the 4, which then also goes through the 2. So maybe the first equivalent circuit I would write would be to say, since it's got to go from the 1 through the 8, that would be discharging through a 9 across the top. And then this would be discharging through a 6 across the bottom. And then, maybe a little harder to see, but the current that comes out of here and splits can go either the 9 or the 6. So the 9 and the 6 are actually in parallel with each other.
Oh, okay. Okay, that's interesting.
Okay, and so that was probably the magical step for you. So to get that equivalent resistance, I have to take the reciprocal of the 6, the reciprocal of the 9, and reciprocate that. And so that's probably somewhere around a 4, if I'm guessing. .6. So this would be discharging through the equivalent of 1 resistor with a resistance of 3.6. So let's see, let me back to the question. If the battery is disconnected, over what time interval does the capacitor discharge to 1? Okay, so the 1/10 of its initial. The voltage as a function of time was equal to the initial value times this e to the minus, and then there's our time constant, this RC. And that's why, and I think you got a clue for it, so I'm just going to finish up here, but I need to get that time constant, RC. So the R is why I went through and got what this is equivalent to, 3.6 ohms, and the C is 1 microfarad. So this is going to be 3.6, and the micro is 10 to the minus 6. And the ohms and the farad, maybe it's not so easy. Maybe it's worth going through. Remember, an ohm is a volts over an amp. Remember, a farad is a coulomb per volt. So the volt would cancel off.
Okay.
And also remember that an amp is a coulomb per second. So the coulomb.
Oh, yeah. So that just becomes a second.
Yeah. And so the reason we call it a time constant is that, mathematically the units come out to be seconds. And of course, physically it's a measurement of the rate and how much time it would take for this capacitor to discharge, not completely. One time constant would be leaving 37%. So it's the time to discharge by 63%. Okay, so we're asked to solve this. So you're asked to say, when will we get 1/10 of the initial voltage? Now, the initial voltage is 6, but I don't even think we need that because they're just going to cancel off. So I'm going to take the 1/10 and write it as a decimal. And then I'll go e to the minus t, and for the time constant, I'll put 3.6 times 10 to the minus 6 seconds. And now I've got to go back to my algebra class to solve for time, and I'll take the natural log of 0.1, because then that'll be a negative t over a 3.6 times 10 to the minus 6. So the time would be, I'll put the negative over here. I'll put the 3.6 times 10 to the negative 6 also over here. And then I'll put an ln of 0.1 and grab a calculator. So negative 3.6 times 10 to the negative 6 multiplied by the natural log of 0.1. And I get a time of 8.29 millionths of a second. So, yay, there's my answer to B.
All right. That makes much more sense.
Okay.
I think it was that parallel step, because I recognized that they were in series, but I didn't see parallel. I'm sure if I just redrew it, I would have seen it.
Yeah. It's when they're in parallel, but there's something in between them, or when they're in series and there's something in between them, it's kind of hard to notice. So it's a good lesson to learn because they know it's a hard lesson for students to learn, so they'll throw that in there in a problem here or there.
Yeah.
And I guess that's the whole point of the homework, to keep practicing on these. And I just wanted to check. Maybe you already know the answer. Was that the right answer?
Let me check.
I think I got it here. 31 B. Oh, I'm on the wrong chapter. I'm in chapter 27.
Let me check. Yeah, 8.29 microseconds.
Okay. 8.29. Yeah, I see it now. Nice. And then the RC time constant was good too. Yeah, good. Nice. Now, ready? Oh, let me click back over here and see if anybody's thrown anything up in the chat. Yes. Oh, you told me how to pronounce it. Timmy? Oh.
You did it.
Oh, thank you. Okay. All right. All right. So chapter 27, number 13B, you say, I tried to use R equals
No.
Oh, row. Oh, I see. Okay. Yeah. Okay, but I'm not getting the same result as the answer. They just used mass, volume, and density relationships. Huh. All right, well, let me look that one up because I'm not sure what exactly your difference is, but I'm going to also write this. And so number 13, we'll see how far we go, but the time is 4:10. Okay. So what's this, chapter 27? And that means I need to go back a chapter. Okay, good. Number 13. Make it 100% again. Oh, suppose you wish to fabricate a uniform wire of 1 gram of copper. If the wire is to has a resistance of a 1/2 ohm and all the copper is to use, what would be the length and the diameter? I'll tell you what, I'm going to run through this because I think I have a feeling what you did, the way you asked your question, and what I'm about to do are kind of one and the same. And so I guess I'll put that as the better way, but then I'll jump over to what the heck the author did and see if there is something different about our two solutions, okay? But okay, so here's what I would do first. I would start off as exactly you did. I would say the resistance is rho times the length over the area. Okay. And of course, if I put in what I know that the resistance is to be a 1/2 ohm. The resistance of copper, or resistivity of copper. Let me just scroll through the book. I should probably know that. I do it so often, but I don't. 1.7 times 10 to the minus 8. And so then we've got length over area. So that would be my natural first step. And I would just say, okay, at this point, I have an equation, but I have two unknowns, its length and its area. Okay. I'll go back to the question here. Make my 100% again so I can read it. Now, the other part of this, though, is they gave me I have 1 gram. So I would go density. And here's where I'm going to run into some troubles because the traditional symbol for density is rho. And I use that up here, but this is the resistivity. And so I'm going to just put a little subscript between each of one. So this was the resistivity, which uses the Greek letter rho. And this is the density, which also uses the Greek letter rho, but I'm going to put density. So density then is of course, the mass over the volume. And here's kind of the key step. I know the mass is 1 gram, although I'm going to write it as kilograms, because the density is probably listed in kilograms per cubic meter. And so then I'm going to put the volume, because if you're talking about a wire like this, it's like a long skinny cylinder, so its volume would be its length times its area. So now I just got to get the density of copper, and I think I'm kind of getting to your question. I need to go back to see exactly what you were asking, but I need to look up the density of copper. And you can either do it on Google, but I'm just going to go to the textbook because it's chapter 14, if you guys remember from the last chapter in Physics 121, where we get into the fluids and we start working with density. This is where the author gives a lot of density. It's in table 1 on 14.1. I guess I'm at page 391 in the textbook. And it says right here that the density of copper is 8.29 times 10 to the third kilograms per cubic meter. And so I'm going to rewrite this as 0.001.
And when you're getting this, that's from the survey book.
Oh yeah, and that's it's table. Yeah, it's in the survey book on the fluids. But let me also emphasize that you could just type in Google, what's the mass density of copper, and I would assume that the OpenStax. I haven't got as familiar with the OpenStax one, but I think the first 14 chapters match. So I'm betting that table 1 of chapter 14 of the OpenStax is a table on the densities.
Isn't the OpenStax 2 volumes though? Like the second volume is this class?
Oh yeah, so excuse me, it would be volume 1, but still chapter 14, yeah. Because volume 1 starts off just like the survey. Chapter 1 goes with 1. And actually they're kind of switched. In the OpenStax, chapter 2 is the same as chapter 3, and then they switch. So the 2 and 3 are switched, but other than that, chapters 1 through 14, even further, all the chapters in the first volume are identical to the survey. So it makes it kind of easy to compare the two. But then the OpenStax goes to volume 2 and they start counting over again. So even though they're exactly the same order, they start over again. That's why when I send out that information, I say something like, for those of you in the survey book, use chapter 28. Those of you in the OpenStax use chapter 10, I believe is how it compares. So the first 14 are the same, and then they start over. So I guess what I'm trying to say is chapter 15 in survey is the same as chapter 1 in the second volume of the OpenStax, but they all compare. Okay, so then back to this, I would say now I have these 2 equations with the 2 unknowns, which are the 2 questions that say, okay, what is its length and what is its area? And I'll finish solving it here, but I think you asked something specifically about it. You said, let me go to your question. Oh, I tried to use, but I am not getting the same result as the answer that they used, mass, volume, and density.
So yeah, basically, I try to use a new formula we learned this chapter, but they use the mass density equal to mass over volume, and my answer doesn't match theirs.
Okay, so they did it like I did it. Is that what you're saying? Because I used that.
Yeah.
And then what did you use?
The one above.
Okay, and then what else? Because there's 2 unknowns.
But you know L, so.
No.
But,
whoa. Hold on. Tell me how you got L.
From part A.
Okay, how'd you get that in part A?
You determine L in part A.
How'd you get L in part A? This is about as far as I can get in part A.
But the part A is asking for the L, so you will get it eventually.
Oh, okay, yeah, but I guess, okay, so help me out here. my first equation I write down is this one, which has an L and an A. So this equation by itself, I cannot get L, which is why I went to this equation. I wasn't even thinking about A or B yet.
Yeah, and I combined the first equation with the second equation, and I got L.
Okay, so you did these two equations?
Yes.
Okay, so I'm going to do that too. And okay, so let me do that. And that's actually what the author is doing. Maybe I'm going to do this. I don't know if this is the best way to solve it, but I'm going to divide the equation, see what happens here. I'm going to go 0.500 equals 1.7 times 10 to the negative 8. And then I will have a L over A. I'm going to divide it by the second one, 0.001 equals 8.92 times 10 to the third L times A. And I guess I like that because the L's are going to cancel off. On this side of the equation, this will go 3 decimals, so that'll be 500. On this side of the equation, there's already an A downstairs, and that would be the equivalent of downstairs. So that'd be A squared. And then in the numerator, I would have 1.7 times 10 to the negative 8, and I would divide it by 8.92 times 10 to the third. So this would be 1.906 times 10 to the negative 12. I take that number and divide by 500, puts the A squared over there. And if I take the square root of all of that, I get 6.17 times 10 to the minus 8 square meters for my A. I think that was the question B, what is the A? And then once I know that, maybe I'll come back to this first equation. There's the A, so I'll move it to that side. So then I will multiply it by the 0.5. Then I will divide it by the 1.7 times 10 to the negative 8. And that's going to be my L. So my L is 1.82. And now I guess I should swing back into the solutions here. This is back to chapter 27, number 13, and see what they got. They got a length of 1.82, good. And they got an area oh, hold on. They didn't do area. Did the question ask for diameter? Maybe.
The first question asked for length. The second question asked for the diameter. Yes.
Yeah. Okay. So I need to keep going with this. This would be pi r squared. So let me come back to my calculator. So moving up to that answer. So there's the area. If I divide that by pi, that would be r squared. So if I take the square root of that, that's r. And of course, if I double r, I get the diameter. So diameter equals 2.80 times 10 to the negative 4 meters, which I might write as, I'll make it smaller, which would make that one bigger. So it'd be 10 to the minus 3. So that would be millimeters. Oh, and then if I make it bigger, that would make that micrometers. They did micro. Yeah. So anyway, so I'm glad to see that we're getting the same thing there.
But when I approach it, I just convert A equal to M over rho times L in the first question. So I didn't calculate A at all.
Okay,
And
good.
then when I got the length, I just used the first equation from this chapter again.
You use this equation twice?
Yeah. Since we know L is, we know L, we know rho R, the resistance, see? And we know the value of the resistant. Then we can just get A, right? If you go up to the first line,
Okay, so my very first line is right here.
yeah,
Okay.
you know L already, so you can get A that way.
No, but how do I know L? That's where I'm lost. I didn't figure out what L is till I got all the way down to here.
Yeah, but I didn't calculate A in my process.
Okay, but I'm still struggling with kind of the bigger mathematical idea that with two unknowns, you need two equations. And and you're telling me you got this one.
I got L from the first equation already, but I didn't do the approach you did. So basically, I set A equal to M over rho as density times L.
Okay, so you just rewrote this. I get that. So let me just write that. Okay, so you want to write A as rho L over R.
Yeah.
Okay. Then what are you going to do?
Then you substitute A is equal to mass times mass divided by the density times the length.
So then you are using this equation. That's that equation.
Yes, but I didn't use it.
But you still have A in there, and you basically get rid of it in this way.
Okay. So I'm going to do exactly what you said because I'm really kind of curious here. All right. So okay. So you took this equation and rewrote it as A equals rho L over R. Got it. But it sounds like to me you also took this equation, which is mass. Hey, how come my phone went off again?
It's still working.
Oh, is it?
Yeah. Seems to be. Yeah.
Yep, it's working just fine.
Okay. Maybe I bumped something on my laptop. Oh, I did. Okay, good. My sheet of paper when I moved it in my laptop. Okay. But yeah, it was fine for you guys and on my desktop. Okay. Okay. So, but you guys got me really curious on this now. Okay. So you did this, and then the second equation. This is the mass. I'll put a capital D for density, and then the length, and then the area, right? So if I heard you right, Timmy.
Yes, you take the A out, which will equal to M over DL.
Good.
And then you substitute that A into the first equation.
Okay, so M
over DL.
L equals rho L R.
Yeah, that's how I calculate L.
Okay, and that should give you, did it give you the right answer?
Yes.
Yes.
Oh, okay, so I would say we've done the same thing so far.
Mm-hmm.
Okay, so, and you got the right answer, so you're happy with that.
Yeah, but for the second question, instead of using V equal to M over D, I used the first equation, yes, to get A.
Yeah, okay. Okay, so it wouldn't matter which equation I used. Did you get the right answer?
No.
Oh.
That's why.
Okay, let me pick that up. All right, but you should have. Everything you said is sound logic. All right, so I won't bother to calculate this out because you said you got this number and agreed. Okay. So let me use it over to here. So my area should be, and then this is the resistivity. That was the 1.7 10 to the negative 8.
Yep.
The length is the 1.82. And the resistance is a 1/2 meter. Okay, so if I grab my calculator, 1.7 times 10 to the negative 8 times 1.82 divided by 0.5, I get an area of 6.18 times 10 to the negative 8. And I can keep going if you would like, but this is what I got up here.
Got it. It must be the rounding then.
Yeah, maybe there's some rounding or you hit a wrong button on the calculator, but your logic is sound.
Okay. I
Yeah,
should share that part.
yeah, okay. Yeah. So just to make it clear, yeah, the author solved it for R and put it into that one, but it wouldn't matter if you put them in that one. And that's what you did. You put it here and it should have came out right. Okay.
So just real quick, I mean, you're actually solving for A in this. For me, when I was solving the problem, I actually just bypassed A entirely and just used it as a variable, and then when I replaced it, at that point, it became irrelevant. I don't think I ever touched it again, even in part B.
Well, in part B, you got to get diameter, so you don't have to solve for A, but you still got to solve for diameter.
Right.
So you could ignore this and then set it equal to pi times diameter squared over 4. And never solve for A, I think is what you're saying. So did you go right to diameter or did you go to radius?
I think I did the formula for radius and then just put 2 in front of it, times 2 in front of it. Because
so you didn't go this far. You just went pi r squared and equals to this. Sure, fine. Because you're right, they don't ask for area. So why calculate it? Except I will say, sometimes it's easier to have little baby steps to get all the way through. I don't know if you've ever been in one of these endurance sports like running a marathon, but how far is a marathon?
Too far.
If you say 26 miles, it's a long race. But if you say one more step, anybody can do that.
Yeah, closest I ever got to that was swimming. Totally different beast.
All right, well, how far is a 1650? Well, it's one more stroke.
Yeah, I get that.
So there's something to be said about taking this and making it into simpler problems. All right. Oh, and then, okay, next here on the list, Zach. Okay, yeah, okay, good. And you and everybody else, feel free to chime in. And Zach, you were just saying, hey, I had the same trouble. So good. I think we answered that. Daniel, okay. When you get a chance, could you please explain the first part of 13? Now, the first part of 13. Oh, in chapter 28. I was gonna say we did 13, but that was a different chapter.
Yeah.
Okay. All right. So let me write. Yeah.
I couldn't figure out what to do, so I just looked at the solution really fast. And
Okay.
the 15 minus 7I1, that makes complete sense. The thing I don't understand is why he's multiplying the other two resistors together for like the I2, unless there's something I'm missing.
Chapter. Well, let me see if I can kind of figure that out with you. So chapter 28, number 13. Let me scroll to number 13. Oh, this is the one we were doing before the break, right? Were you here?
I think I had to go
Yeah.
do
No,
something.
no. Wait. This is the one we were talking about the photoresistor and that
Oh,
was you.
sorry, 16.
Oh, 16. Okay.
Yeah, little different.
Yeah.
I
Okay.
took the
Okay. So
wrong number.
let me go down to 16. That's fine. Okay. So let me cross this out. 16, and it says the ammeter shown in the figure reads 2 amps. Find current 1 and current 2 and the EMF. Okay, so let's kind of go through our Kirchhoff's laws again. This is the 15 volts. It goes through this resistor, which they say is 7 ohms. And in that diagram, it hooks around here, and they are saying that this is 1 amp. There's a center branch that has 5 ohms, and this is the branch that has the ammeter in it.
Mm-hmm. And that equals, it reads 2 ohms or 2 amps.
2 amps, okay. But the key, well, I don't know if this is the whole key to it, but they're trying to say that if this is 2 and this is 1, they're going to merge right here at this node and flow together and go through the ammeter.
So that'd be I3.
Okay, but at this point, maybe to keep it easier on myself, instead of calling it I3, I know it's 2 amps because that's what's the reading on the ammeter. If I call it I3, I'm going to think I have 3 unknowns.
Okay.
So I'm just going to say I1 plus I2 is 2. Now, I'll refer to this then as equation number 1. But you can see that, like the other problems we did before this session, is that I now am going to have 3 unknowns. They're not all currents like they were in the other examples I was doing with you, but the 3 unknowns would be current 1, current 2, and this EMF of this lower battery.
Mm-hmm.
Okay. Now, I'm going to try something. Tell me if this works. I'm going to do something a little more advanced than just kind of the basic write out the equations and solve. And watch this cleverness, if you will. If 2 amps are going through this branch right here, okay, then this change in voltage would be 2 times 5. That's 10 volts. That means also that up here, these 2 must be 10.
So how do you know it's 10 volts?
Ohm's law would be current times resistance. Resistance is 5, current is 2.
Oh, okay, I see.
Now maybe I was trying to do too much. I'll just do the loop. All right. So here's A, here's B, here's C, here's D. Let's do the loop. A, B, C, D, back to A. So from A, I would go plus 15. Then I would go minus 7I1. There's the resistance and the current is I1. That would get me to B. From B to C, nothing really changes. Then I would go from C, and then this resistor right here is 5 ohms, and the current is 2.
Okay,
So that's
that
a decrease of 10, and that completes the loop.
okay, that's what I was missing there.
And
Okay.
so I'll put the 7I1 over here and leave the 5 over here. So this would be 5 over 7 is I1. 5 divided by 7 is 0.714.
Okay, that explains where I was lost. I can figure it out from there, I think.
Yeah. Good, but out of my own curiosity, then I'll go kind of quick if you got it. Remember that earlier on we said these two have to add up to 2. So I'm going to just say that if I took 2 and subtracted my last answer, current number 2 must be 1.286. And then to finish this, I'll do this bottom loop, which maybe I'll start here and call this E. And so I'll do a loop that is E, F, C, D back to E. So from little bar to big bar, there's the E that I'd like to find. I'd be going with the current, and this resistor I didn't write down. Let me find that picture. This was 16. Oh, so this is a 2 here. Okay. So this would be going with the current, would be minus, and it would be a resistance of 2 and a current of 1.286. That would get me over to C. From C to D would be that minus 10 again, because it would be 2 amps times 5, and that would finish. And so my EMF, when I move this over, would be 10, and then it would be plus 2 times my last answer, and give me a 12.57 volts. Yay! So, and maybe a quick looky here. Did I get back to chapter 28, number 16, and good, they all match. Nice. All right, so I want to make sure I get to all you guys' questions. I see it's getting kind of late, but there was a bunch in here. If you have more time, okay, I do. I also want to.
I got it.
Oh, good. All right.
Yeah.
Congratulations. All right, 22 and 27. All right. 100 looks like 100 checked out, says thanks, right? Oh, and then you write, I don't have to do problem. All right. Oh, okay, good. That closed up pretty quick. And I guess we're a little past time, but I'll just ask again, let's make sure everybody is at least ready to go to the next step. I'm sure you still got a lot more homework to do, but any more questions before we wrap it up here in this session?
This is less of a homework problem and more of just a schedule question. Just looking ahead,
Yeah.
on the calendar, it shows that we have 2 labs due on Sunday. I just wanted to make sure.
Oh, I hope I fixed that. When's the last time you looked?
Not last night, but I'll double check right now just to be sure.
Yeah, and I'm gonna too. But you only have 1 lab due, and you remember one week, the week we were originally supposed to do Ohm's law, I went in to make the video, and it involved the computers, and they had to taken the computers apart thinking nobody needed them, and I was bummed. And then I had originally told you guys, we'll just do 2 the next week and catch up.
I found it. It is updated.
Okay, good.
Okay, good. Yeah.
And so I
Did they
shifted
take that?
everything by 1 week, and I'm still not 100% sure what to do, but this whole online teaching stuff is new and challenging, and I'm thinking maybe we'll just end up, dropping the last lab at the end and just say, well, we did it, or some.
Why did they take the computers apart? Just because
To be more-
it's online, so figured they could use the parts for something.
I should be more clear. Yeah, I made it sound like they took them all apart. What they do every summer is they create a new image. And what I mean by that is they update all the software, and the program I've been using is called Logger Pro and Graphical Analysis. So they updated it, but something went terribly wrong. Because when I went to use it and to plug the hardware in, it didn't work. So I called the help desk. I go, well, it's okay. I'll just grade papers while they come and fix it. Well, because of this pandemic, nobody's on campus. And nobody came, and nobody came, and nobody came. And I called them a few times, but everybody I called, they were at home. And I finally just said, well, all right, it's getting late in the day. I'm gonna head home myself. Maybe tomorrow or the next day we can get it fixed. Anyways, turned out it took all the way until Friday before somebody actually came to campus. And it turns out really what it was is when they did the update, they did not install the drivers for the USB. So when you plug something in, there was no USB connection.
Oh, I see.
So it was just an oversight. Anyway, so they fixed it on that Friday, and then I came in on Monday and I did my recording thinking that I would do 2 that week. And then I finally just said, we're a week behind, and and it just seems like, I don't know about you guys, but everything I try to do on campus is just, even at home, it's just harder because of the pandemic. So sometimes it's just maybe more of progress over perfection. So anyway, that's what ended up happening.
Well, I'm gonna rest from physics for a little bit because I've been doing it all day. So
Yeah, that happens. You get to some point, you just want to kind of say,
hope everyone has a good weekend.
all right. You too.
Bye.
I'm
All right,
signing
bye.
out as well. Thank you, Dr. Yang.
All right. Good seeing you.
Thank
Take
you.
care. Bye.
Yeah.
You too, Zach.
Hi.
Yeah.